Water. It's literally everywhere, right? Covering over 70% of our planet's surface, and, well, it's essential for all life as we know it. But have you ever really stopped to wonder where it all came from? It turns out that's one of the biggest questions in planetary science. And trying to answer it is like a cosmic detective story that stretches back billions of years. So let's dive in. Okay, so here's the mystery, the central paradox we're trying to solve. When Earth first formed, about 4.5 billion years ago, it was just this molten ball of rock. It was way, way too hot for liquid water to exist. Any water that was around should have just boiled right off into space. And yet, we look at the geological record, and just a couple 100 million years later, bam, our planet has vast liquid oceans. So how does a fiery, dry world get soaking wet so incredibly fast? To crack this case, scientists have had to become cosmic detectives, piecing together clues from literally all across the solar system. So this is it. This is the big question that's been driving decades of research. If the water wasn't here from the get-go, it must have been delivered from somewhere else. The investigation has to start by lining up all the possible sources. All right, it's time to meet the suspects in this planetary whodunit. There are really three main candidates for where all our water came from. First up, suspect number one, comets. Now, for the longest time, these guys were the prime suspects. I mean, it makes perfect sense, right? They're basically these giant, dirty snowballs, just packed with water ice and organic stuff. The theory was that they just pummeled the early Earth, delivering all their water in a period of intense bombardment. Then we have suspect number two, asteroids. Specifically, a certain type called carbonaceous chondrites. Now, these are really ancient, water-rich rocks that mostly come from the asteroid belt. They don't have quite as much water as comets, pound for pound, but there are a lot more of them, and their orbit made them a really likely candidate for colliding with the young Earth. And for our third and final suspect, well, this one's a bit of a twist. What if a big chunk of the water was actually here all along? This theory suggests that the ingredients for water were locked deep inside minerals in the Earth's mantle, and over billions of years, this water was gradually released to the surface through volcanic activity. Okay, so we've got our suspects lined up. Now, like any good detective story, we need some forensic evidence. And lucky for us, water carries a very unique chemical signature. It's like a fingerprint that lets scientists trace exactly where it came from. And this is the key to the entire investigation. It's called the deuterium to hydrogen ratio, or DH ratio for short. So deuterium is just a heavier version of hydrogen, and the ratio between the two, it acts like a perfect chemical fingerprint that changes depending on where in the solar system the water originally formed. So the mission becomes pretty simple. Compare the DH fingerprint of our suspects to the fingerprint of the water right here in Earth's oceans. And when you lay out the evidence, the results are, well, they're pretty incredible. The DH ratio for most of the comets we've measured, it's almost double what we see on Earth. It's a clear mismatch. But the carbonaceous asteroids, their chemical fingerprint is a near-perfect match for our oceans. We also see that hydrogen from the early solar nebula is a partial match, which kind of hints that it's also part of the story. But the evidence points overwhelmingly toward asteroids as our primary water delivery service. So based on all that fingerprint evidence, the scientific community has pretty much reached a verdict. It wasn't just a single culprit, nope. It was a combination of sources that came together to fill our oceans. And, recent space missions have basically sealed the deal on this. The Rosetta mission got up close and personal with Comet 67P and confirmed its water was a definite mismatch. But then missions like Hayabusa 2 and OSIRIS-REx went out, grabbed actual samples from asteroids, and brought them back to Earth. And guess what they found? Water-bearing minerals with DH ratios that were, once again, a perfect match for our own. That is the smoking gun. So when you put it all together, what's the final recipe for our oceans? Well, the modern consensus breaks it down something like this. The vast majority, maybe 70 to 80%, was delivered by asteroids. Then a good chunk, say 10 to 20%, came from primordial hydrogen that got mixed into the planet as it was forming. And comets, yeah, they chipped in, but probably less than 10% of the total. But, this isn't just about solving some ancient cold case. Figuring out where our water came from is absolutely fundamental to understanding why our planet is, well, alive. Think about it. The arrival of all that water was a total game changer. It lubricated the planet's crust, which is what allows for the slow dance of plate tectonics. It acted like a giant global thermostat, helping create a stable climate for billions of years. And, most importantly, it gave us the universal solvent,
the chemical soup where the very first sparks of life could actually get started. Without this cosmic delivery, Earth would just be another barren rock in space.
This really puts it all into perspective, doesn't it? The water in your glass, the rain falling outside your window, it has a history that is truly cosmic. Every single drop is a tangible link between us, right here, right now, and the very formation of our solar system. And that, of course, leaves us with one final, incredible thought. The processes that brought water to Earth, these icy asteroids, this primordial gas, they aren't unique. They're actually pretty common throughout the galaxy. So if the ingredients are everywhere, the real question isn't just how our blue planet came to be, but how many others just like it are out there waiting to be discovered.